Hello, everybody. I'm really thrilled that Beth and the Goldtown Nickelodeon invited me to come and join their National Science on the Screen event. And they said, and you get to talk about my favorite subjects, the ocean and the tools that we use to study the ocean, especially submersibles. So I will be introducing you to some basic concepts about the deep sea, fundamentals for those of you who have not been in school a while, just to remember some of the basics. And then we're going to jump right in and talk about a plethora of submersibles, manned submarines or woman submarines, as you wish, we use to conduct research in the deep ocean. I'll then, if time allows, I'll touch on some recent findings in the last 10 years, findings in the deep ocean in Alaska, as well as in some of the deepest parts of this single ocean that we have that covers our planet. And she did mention a number of things in her introduction, but one was bathymetry. So I wanted to first point out that this is the latest, greatest bathymetric chart of Alaska. What is bathymetry? It's measurements of the depths. It's like your topographic map, but for the depths. And in this case, the depths here, the red is deeper than these lighter yellows and greens. So here we have the outline of Alaska, the Aleutian Archipelago, and Southeast Alaska. Down here, we'll be talking about this area. What student in the room knows what this is? The Aleutian Trench, the Aleutian Basin, the Bering Sea Shelf, Bering Strait, and up into the Arctic Basin. So we'll get back to focusing on that after we have a good chat about some of the most awesome submarines out there. Okay, so we do indeed live on the blue planet. Roughly 71% of Earth is, the skin of the Earth is covered by ocean. Salt water, salt made up of 8 salts, and water in various mixtures and densities. However, that's just the skin. The volume of the Earth's oceans is really what tells us what a massive habitat it is. The deepest place in the sea is over 7 miles, about 11,000 meters deep. And so think about that in the dimensions. Think about Everest and Denali upside down in the water, shapes. That volume creates about 94% of living space for all of Earth's organisms. That's most of the creatures on our planet. Blue planet, most organisms in the ocean. The oceans also have the longest mountain chains, which is they're called seamounts. We also have massive ridges, and yet very little of the seabed has been explored. The seafloor, less than an estimated 5%, but in that whole volume of the sea, the different habitats that are in this really highly stratified and structured water column, we have very little information about, though we are learning. And certainly most of you are aware that we have better maps of the moon than we do the seafloor. Why is that? Because the atmosphere is very thin, and we can use various types of wavelengths to map the shapes and features and shadows on the moon. Ocean water, very dense, very heavy. It attenuates not only light waves from the sun, or light beams from the sun, but also any other sonar equipment. It's very attenuated, so we can't cover large areas efficiently. If we could, we would know much more about our ocean than we presently do. Okay, a quick primer on how deep is the sea. We often are most familiar with this uppermost continental shelf, this illuminated zone called the epipelagic zone or the sunlit zone. Up to about 200 meters, sunlight will penetrate, though it's not the full spectrum that we see from the sun. The longer, more powerful wavelengths of light penetrate deeper. You see these deep purple colors in the deep ocean, and some of the smaller, shorter wavelengths are quickly absorbed and attenuated in the salt water of the sea. So it gets dark, pretty shallow. By 1,000 meters, very, very little light. Then we have the bathypelagic zone, or the midnight zone. Got a little ctenophore hanging out in there. And that's off the continental shelf, down in the slopes. We have this deeper body of water, 1,000 to about 4,000 meters in depth. And now we're getting down to it. We're going to think about this movie a little bit later, The Abyss. We're down into the abyss. The abyssal pelagic zone, about 5,000 meters, okay? On the entire planet, the average depth of the water is right about here, right about 4,000 meters, okay? But let's just carry on down. So now we have the vast ocean basins, right around 6,000 meters deep, and then dive deep into the trenches, the hadal pelagic zone, where there's hadal creatures and fantastic species and much to be learned about geology and chemistry of our planet down at this depth. So for those of us who think more in feet, we're now at over 36,000 feet. So the deepest place in the world's ocean is located where? Do any of you students know? Students? This student up here, you know, sir? The trenches. Do you know which trench is the deepest?
I forgot the name, but it's the one in the Pacific Ocean.
It's one in the Pacific Ocean. Yes, ma'am?
Mariana Trench.
Mariana Trench, exactly. Okay, and does anyone remember the deepest trench in Alaska? We talked about it in the first slide. Located south of that arc of islands? Aleutian Trench. Okay, so the deepest point in the world's oceans is here in Marianas Trench. Actually, a section of Marianas Trench that's super deep called Challenger Deep. That's the deepest place we know of. It's about 10,860 meters deep. The Aleutian Trench, insofar as it has been mapped, and again, it takes quite a bit to conduct sonar maps of the deep sea, but as far as we know, the Aleutian Trench is somewhere between 7,800 and 8,300 meters deep. Still pretty deep. Take Denali, straight down. That's just south of Kodiak. Is one of the deepest places in the United States. It's awesome. Have we been there? Well, let's talk about the history of submarine research in Alaska. Okay, first features of the deep that influence marine life. Moments ago, I talked to you about the penetration of sunlight. Okay, seawater absorbs and refracts and attenuates light very, very rapidly. Therefore, all those creatures that depend on the full spectrum of sunlight or even particular wavelengths of sunlight, like photosynthetic organisms, the microalgae that are the base of the food web for the ocean, they need to live where? They need to live up in the shallower waters where there's lots of sunlight. So this is only 200 meters out of 11,000 meters. A very thin skin of our planet has a photosynthetically active productivity or primary productivity happening up there. Okay, we also have some other features of the deep that influence marine life that occurs there. The ocean tends to be highly stratified in terms of temperature and salinity, so which combined affect the density. The average temperature of the surface waters can vary quite a bit. In Juneau, Alaska today, it's about 5.5 degrees Celsius. And near the equator, it can be as warm as 24 C. In Juneau, in the summer, we get about the top 10 centimeters. It'll get about 15 C occasionally. But immediately below that, it drops quite abruptly. And you can see this thermocline, or this area of abrupt reduction in temperature right here. So we have surface temperatures around 1,500 meters can be as warm as about 8 degrees C, but most of the ocean is somewhere around 3 degrees Celsius. It's cold. And up in the Arctic, it's colder because seawater freezes at what temperature? Anybody know? Yes, sir? 30 degrees Fahrenheit, negative 1.8 Celsius. Somebody knows their science, right? So it freezes at not 32 Fahrenheit, but below that, because salt water is more dense, freezes at a lower temperature. So it can be in the Arctic. This line continues and is over here. So we're below zero in Arctic waters. It provides for very, very challenging for life that lives there, other than humans. But it's definitely challenging to do research in temperatures like that. Another major feature of the deep ocean, one that's kind of scary to think about, is something we do not endure, or at least we don't feel that we endure at surface. So we have the pressure based on the weight of the seawater. right? And pressure can be tremendous. Okay, we have a lot of creatures that adapt to pressure. Even salmon and other species have to adapt to changes in pressure, but there are some very, very deep sea fishes that adapt to pressure in various ways. So for every approximately 10 meters of water, we're increasing 14.7 psi. So at these depths, we're up at some pretty high pressures just at a depth to which humans can free dive or scuba dive. We can tolerate roughly 3 or 4 atmospheres of pressure on our body if you're healthy in general. We do have problems at those depths. At 3 to 4 atmospheres of pressure, we can have problems. If you're dehydrated, you can have a difficulty with gas exchange, osmotic challenges. But that's not very much pressure for the ocean. There's much more pressure down there, and when you get down to the Marianas Trench, over 15,000 psi, 15,000 pounds per square inch. I mean, it's a tremendous, tremendous pressure. So how do creatures adapt? Various ways. How do we deal with those pressures if we want to go into the ocean? We have to use our brains and technology to try to overcome that. Many species occupy a very specific zone of the ocean, be it in the sunlit euphotic zone, the deeper bathyl zone. Species are adapted for occupying these spaces. Squid, for example, can tolerate very low light, ultra low light. They also can tolerate low oxygen. There are some areas in the stratified ocean where the oxygen levels are quite low. And squid are very adaptable to that. Squid, which are a mollusk, just like the octopus. Okay, and then other species are adapted for this darker part, not only by being able to withstand pressure, but what else? What other adaptation? What kind of fish is this that's adapted for deep sea life? Lanternfish. What's another name for it? Anglerfish, exactly. And they are adapted for a lightless environment. Many other species are. In fact, some of those adaptations might be virtually no eyes. I mean, who needs eyes if you're not a visual predator? In fact, this is the female of the anglerfish, and the male of the anglerfish of this same species would be about this large. So these anglerfish, just like an angler, just like a fisher person, they're out there, holding their rod out, illuminating that lure, if you will, and they can use that for communicating with their mates. They use that light for communicating with prey, to draw in prey, and then snap it. And we're going to talk more about bioluminescence in a moment. It's amazing. And it ends up that, of course, this creature is not creating that light. The fish is not creating the light. Does anyone know what creates the light? You do? The sun? In this case, it's a chemoreceptors, and it's bacteria. So this fish is a vertebrate like us, has a backbone. It's a complex animal, highly evolved, but it has a special partnership with bacteria that live in that are making that lure light up. The big question is, how does that creature communicate with the bacteria? And we'll get back to that in a moment. Okay, and then other fishes are very specially adapted. They have lights on the body cavity, and they're able to withstand phenomenal pressure, extended periods of darkness, and have unique features for attracting their mates. Because if you're down at the depths and it's a very vast area, you need to have special chemosynthetic chemicals and lights and other techniques for attracting your mates so you can reproduce and continue your species. Even though these species often occupy specific zones, in the entire ocean, every single day, the largest migration on Earth occurs, right? Every day. Billions of creatures are migrating, what we call diel migration, vertical migration. Many species, whether it's like krill that you see up here, and many larger animals, they migrate for different reasons. They migrate for avoiding predators or come up from the dark to reach prey. There's vast migrations. There's for what we see on the surface and what we think about in the deep, dark abyss might be very, very closely related. They encounter one another, and they therefore also encounter us, and we'll get back to that a little bit later. Okay, adaptations in the deep sea. So we don't have these special adaptations, so we need to use a little bit of physics. And what is the perfect shape for withstanding pressure? Yes, in the front row. A sphere. A sphere, exactly right, because every force of pressure is exerted equally on a sphere, so it's very difficult to crush a sphere. Would you like to finish the talk? Come on. Doing great. Okay, so this is William Beebe and his sponsor, colleague, Barton. Okay, and this is the bathysphere of 1934. These guys were incredibly creative. You know, break out your welding rods, let's build a sphere. Okay, ready to go? Yep, and down they went. And they spent quite a bit of time in there. Quality time in a 4-foot diameter sphere. They had a wooden bench in there. They had little snacks, a little bit of water, and they were always tethered. So basically they're off of a ship over the side of the crane and just hanging down there in the water column. And they broadcast on the radio all across the country. Awesome. Back in 1934. So we've been at this for some time. Every single submarine that goes below, well, it depends on what they're composed, what they're built with, but almost every sub has this same spherical design for the humans inside. Okay, they might be huge, like the Trieste, which was gigantic. It filled this entire library. Most of that was incompressible fuel, the flotation system for the Trieste that went to the bottom of the Marianas Trench in 1960 with 2 individuals on board. But even with the Trieste, as massive as it was, the humans were in a sphere. And so we're going to see this same design repeatedly through all of some of my favorite submarines I'm going to share with you in a moment. So the pilot sphere, made of steel or the strongest steel, blends of steel, titanium. Inside, everyone has several basic components, and this is really a short list because those compartments are crammed with tools, lots of tools you have to deal with. Oxygen, CO2 scrubbers to remove what you exhale. We maintain inside the submarine sphere exactly what you're breathing here, or as close to it as we can, which is what percent oxygen? About 20%, 20.8% oxygen. So all the equipment to maintain that, plus all your tools, video monitors and such. Oh, looks like we're jumping. Okay, there we go. So we looked at the depths. Here on this axis are the depths of the sea, and technologically here's the submarines that can reach those depths. Here is the Trieste. Don Walsh and Jacques Picard in 1960 together went to the bottom of the Marianas Trench, and there's that sphere. There's the humans. This is all the apparatus to get them there. Get them there and get them back. And until just a few years ago, this didn't exist. There was only one sub for 50 years that had been to the bottom of the ocean. The captain of that sub is still alive, Captain Don Walsh. Picard passed away recently. But then along came James Cameron, and he built a super custom, tricked out submarine, and he wanted to be the next person to dive to the deepest place in the world's ocean, and he did. And he and Don Walsh agree that they both went to exactly the same depth. And that deal was made in New York afterwards. Anyway, so next we have other awesome submersibles that are not familiar to some of us, the Shinkai 6500 and the Geolong, Japanese submarine, Chinese submarine. They have invested heavily in submersibles and undersea research. Okay, we have a lot of autonomous AUVs that now can go to about 6,000 or even 8,000 meters deep now. What subs can reach the Bathypelagic zone? The United States' best submarine, the Alvin, not quite. Just barely can get there, and that's only after the refit that was just completed. Okay, so then we have research ROVs, but no other submarines can get down to this zone. And then we have the 1,000 meters, and we have more subs that are built for handling this. In fact, here's one right here. This is the sister submarine to the one sitting outside of the Goldtown Nickelodeon Theater right at this very minute. So these were built starting in the late 70s and several other subs. But as far as scuba diving goes, 40 to 50 meters is about all a free diver can dive to. You know, it can go on air, you can go on nitrox or heliox, but overall, you're not going to want to be diving too much deeper than that and be a healthy, productive research diver, that's for sure. So, here's a preview of Jim's submarine. Okay, very unique submersible. James Cameron went to the bottom of Marianas Trench in 2013. I should know. 2013, there's his human sphere. All the rest of this is foam and cameras and lights because he's a filmmaker and he wanted to capture footage of deep sea creatures and add them to his collection of footage, as well as he wanted to contribute to science. So here are those other subs I mentioned a moment ago. The Russian Mir Submarine that was used in filming and exploring the Titanic, as well as the Mirs are the ones that were used less famously in taking a Russian flag onto the Arctic ice, the 4,200 meters, and saying, you know, I don't know if you ever saw that, the great shot of the manipulator putting the flag in the Arctic under the sea ice and claiming the Arctic for Russia. I've been offered a little money to go out and pull it out. Alaskan flag, capture the flag game at 4,000 meters under the ice cap. Hey, I'm up for it. Then I told them what that sub would cost to actually go do that, and then they got quiet. Here's the Japanese sub again in a little more detail, and here's the Chinese Geelong 3-person subs that can go down to 7,000 meters deep. Here's some of our U.S. subs. These are based in Hawaii. They do have a date in the future in Alaska. They go to about 2,000 meters, hold 3 people. These are awesome subs. I've gone over to do some training in these submersibles. Extremely high-tech manipulators and many, many research tools on board for studying not just visually, but taking chemical samples, geological samples of the deep ocean. Very small viewports. Why? They're about 3 centimeters thick acrylic to withstand the pressure. You know, you have to stare out of these small things, but there are very large cameras on board as well, and they just got a new one. And these are awesome subs, and hopefully you'll see them right out here someday on the ship, ready to get out and do some research in Alaska. So now I'm going to talk about some submersibles that have been here over the years. We have had several different research subs visit Alaskan shores. Oh, we've also had military subs. This is the first submarine that I know of in Alaska, and I know of it because the relatives of this Captain Jim Abel have contacted me. Unfortunately, this sub was shot down by the Japanese and is still underwater offshore south of Kiska Island. So it's true, like the Russian Kursk sub, not all submarines make it back. There are, and in those days, they had some pretty huge technological challenges. They're all the way out in the Aleutians, fighting a war, under attack. And if anyone's been to the Aleutian Islands, you know it's some pretty challenging undersea navigation, extreme currents, especially if you're under fire. So this still remains underwater in Kiska with everyone that had been aboard. So this is a small research sub that started work in Alaska back in the 70s called the Nekton Gamma, and they had some pretty early research tools on board, viewports. They did have a manipulator that was manual, and they did some of the first very important research on rockfish distribution in areas where they couldn't use big nets to scoop up the fish, trawl nets too, that are commonly used for surveys. Then we have this submersible. Some of you might have seen in town if you were around about 12, 15 years ago. I actually dove in that sub, as did one other NOAA biologist that was studying crab. I used this submarine in Taku Inlet. I was doing studies of the deep sea basin to look at potential effects of the mine that is up the Taku River, as well as potential distribution of tailings in the deep sea down there. So this thing we call the Jeep of the Deep, over 6,700 dives, thousands in Alaska for many, many years, and they've contributed to our knowledge of many things. They use sonar like this. Some of our first observations of large crab aggregations, rockfishes, and corals came from that Jeep of the Deep Delta submersible, and the many people with Fish and Game and NOAA that spend hours and hours, many days of their lives in that submersible. Tremendous to discover that Alaska in the cold north has these amazing corals. So we also have our hallmark submersible, the Alvin, named after a chipmunk. Alvin has been to Alaska a couple of times, studying the mountains of the ocean, the seamounts, taking a look at life on these fairly isolated undersea islands, if you will, far out in the Gulf of Alaska, and had tremendous findings contributing to our knowledge of biodiversity and geology of these unique forms. Actually, some of their original work led to the realization that these are isolated with isolated genetic populations of fish and crab and corals, and many of the seamounts were so unique that it ended up, several of them were protected from certain types of fisheries that could overexploit the limited genetic populations of rockfish. They also led to discoveries of tiny, delicate crabs and some of our really exquisite deep cold water corals. They also, Alvin did some dives off of Kodiak in an area called toward the Aleutians, between Kodiak and the Aleutians. Dr. Lisa Levin is a phenomenal scientist and did these dives in this area down to several thousand meters deep and documented some of the first known methane hydrate communities, chemosynthetic communities that utilize not the energy of the sun for food, but chemosynthetic processes using methane hydrate. So this is what's called a methane hydrate seep. It's not very unique looking, but these are bivalves we know around here that clams filter feed on plankton. Not so much here. They are utilizing organisms that feed, they're methanotrophic, and they only consume methane for their energy. Methane hydrate is a methane molecule trapped in a lattice of water. And so because it's methane, the gas, it'll come up. Sometimes it's under pressure, it's still cold, you bring it up to the surface and you can show all the grad students how you can have some burning methane hydrate in your hand. This is one of my favorite submersibles of all time, and take note, all of those of you going to see the movie later are going to see this again. She's under disguise. They did some Hollywood things to my baby, the Deep Rover. Awesome submersible designed and built in Canada. And she's 1,100 meters, has some big manipulator arms. She has a great capacity. She has huge thrusters, like all subs or most subs. She's battery powered, and she can go to 1,100 meters. That gets you down there. She's awesome.
How long does it take to get that deep?
It takes about an hour and 20 minutes if you're hard down. But actually, so the deep workers, you run with your feet for the vertical thrusters down. Deep Rover has the actual carriage you're in is one of those old F-16 fighter pilot seats. They literally just put one of those in, and then they have these controls on the arms so to go down and Deep Rover to bottom. You have to hammer down with your arm and just keep going and going. They're going to try to change it. It's exhausting. And you're cold, and you've got about 20 other jobs to do, not to mention life support to deal with. I mean, you have to deal with it. You have to manage it actively. Topside never gives you a spare minute to, not be working on your life support, maintaining your oxygen level, making sure your scrubbers are working, making sure your interior temperature is okay, no water alarms, batteries are good. It's a lot. Anyway, back to research in Alaska. I'm going to show you some work that I participated in working in this area. I've been working in this area for quite a few years on the Bering Sea shelf edge, and we did a couple of expeditions up there in the deep worker single person subs, maximum depth 600 meters. So now we're starting at the bottom, now we're working our way up. These have 600 meter depth capacity, but still pretty deep for working in some of the areas that have never been either mapped or observed or studied in situ. In their natural habitat is the way we prefer to study marine life, just like naturalists around here. You need to see creatures in their natural environment to understand them. People say, why don't you just use one of the ROVs? Those robots are safe. They're easier. They can work 24/7. But you see this? And you see that? Okay. So this is how we think of ROVs. We get a paper towel tube and we go, well, that's, you're going to learn a lot, but you're all the way down there and you can miss so much. Also, you don't have your own mind. You're not down there making decisions, seeing conditions or creatures that you need to examine. Your sampling protocols are very different if you've got a robot down there, which is very useful compared to having humans in a sub. But having humans in a sub means you need your dive supervisor, you need your radio operator guy, you need a huge crew up on the deck to take care of you. You'll see later in the movie, The Abyss, crane operators, #1 friend. They put us in and they take us out of the ocean. And here I am hanging by the crane right at the moment, ready for a dive. And where am I diving to? Into a deep canyon, Pribilof Canyon. This is, so you can see the bathymetry. This pink up here is about 120 meters deep, if you can imagine. And then the rest of this canyon system goes down to about 2,300 meters deep. It's very complex. Some of the canyon walls are very steep. Some of them are very gentle slope, made of different habitat types, rock, sediment, and a lot of methane hydrate crust as it ends up. Here's one of the views of bathymetry of some of the rougher hewn areas. And then this second map, this is not fully mapped yet. This is a vast canyon, the largest undersea canyon in the world, called Szymczak Canyon, and it has several axes and what's called thalwegs or branches. Then, and every one of these, we tried to get in and examine species and habitats, looking at biodiversity, also looking for signs of chemosynthetic processes. Because as we try to model fisheries production, we often think about the photosynthetic, think of the food chain, the big pyramid. We think phytoplankton in the ocean, copepods and on down. But we never add to that equation other sources of energy. So I'm trying to determine whether and how much chemosynthetic processes actually contribute to the overall carbon balance in the ocean by contributing from the bottom up, if you will. During this particular suite of dives, we did over 25 dives, lots of video, lots of samples. I'm going to show you some of the species that we found, some new corals, sponges that had never been documented in this area as well, some of the most exquisite corals we've ever seen in Alaska, some over 2 meters high, including this Paragorgia, which is actually closer to 3 meters high, down to the tiny, tiny little delicate Caraphelia, which is about as large as your thumbnail. So we were able to document not only corals, but the corals that create habitat for so many other species that contribute to the diversity of life down there. We also found quite a number of sponge species. Helmut Leonard was extremely helpful in doing some of the descriptive and taxonomic work on these sponges. There are 2 main groups of sponges, calcareous sponges and those with siliceous spicules. The calcareous sponges in particular, they're the softer, squishier sponges, okay? And many of those contain antiviral and antibacterial compounds. In fact, in the Bering Sea and Gulf of Alaska, there's been a species found and actually tested, screened for antiviral compounds and other for medicinal purposes, and found to have tremendous antagonistic effect against tuberculosis. In fact, the most antagonistic compound against tuberculosis ever tested in the lab comes from Alaskan sponges. We have a lot to learn in the deep sea. We have to invest in the technology to get down there. Other species in this area are one of my favorite. They are tiny, about like this size, and they're called opistobranchs. When I first saw that, I'm in the sub and I was seeing these beautiful little creatures, I couldn't quite determine what they were. They look like sea slugs, for those of you who know the sea slugs, the nudibranchs, very similar. They're a little snail whose shell is on the inside. And it bothered me for quite a while. I couldn't quite key them out. We collected a few, and it ended up, over the next few years, found out that indeed it was a new species. We were working on describing the species, and then those Russians published a paper and said, guess what we found? 1 year before I was able to get the paper out, they did a tremendous job in describing this new species. And meanwhile, we're staring at electron microscope imagery of the tongue, which is a very distinctive shape. The radular morphology is one of the diagnostic features we use to identify different species of these cryptic but beautiful and ecologically very important small snails. Now, why would they be pink at that depth? Any ideas? They stand out to any predator that wants a nice, tasty little snail like this, right? Or do they? Remember? Yes, sir.
Is pink like a warning color to creatures that like to eat it so that they
Pink is a warning color. Pinks and reds are warning colors. And I say, sure, go ahead and eat me, full of toxic, distasteful chemicals. So the only way we were able to actually collect these tiny nudibranchs, you can see actually they have external gills. We could talk about these guys all day long. They're beautiful. There ended up being a lot of fishing debris down there. Ropes, things like that, that these creatures were actually on. Let's see if this is, I wanted to show you one shot, what it's kind of like down there inside the sub as we're looking around in the Bering Sea. I don't think we have audio in here, do we? Can you kind of hear that? So now we're panning around on the inside. You can see pressure gauges. You see oxygen meters. You see this bezel is monitoring my exhale, my oxygen. We've got tools inside. And we're trying to record data all the while and run cameras and collect and maintain communication with the topside and run the sonar. The sound you hear is my manipulator moving out. Always, you know, this is the same kind of thing Cameron has in his sub. You have to constantly monitor everything. You have to be a supreme multitasker and also stay on mission. Anyway, so this is now looking outside. Rather than filming from the camera that's out here, this is looking out. And this is the only time. Giant sponge.
Checking out sponges and corals. Got a huge school of Pacific Ocean perch swimming by.
So this is from the inside camera. We have about 200 hours of underwater footage, some of which local film companies made into films. You're going to see a lot of underwater films later on today, this evening in the abyss. So we're going to move on into just a few more of the results and some images of some of the phenomenal species that are in the Gulf of Alaska and Bering Sea canyons. Tiny crustaceans, new species of sponge. We expect now about 4 more new species of sponge that will be described from some of our recent collections. Exotic life forms like these sea stars that have giant hollow rays. They look like giant puppets walking on, like marionettes, walking on the soft seafloor. They're adapted for life in 4 to 1,000 meters depths. This is what they look like in outside of the camera. This one I was able to collect. They're, again, related to our sea stars, but they're bracingid named Astrocles, occupy very deep depths. And this is another echinoderm that lives on small creatures that are attached to sponges. And again, this is the bubblegum coral or Paragorgia, plus some new species of worms attached to them. And these form huge coral forests in some parts of Gulf of Alaska, Aleutians, and the Bering Sea, as well as the Arctic. And again, the most delicate, tiny corals. And these grow 2 kilometers from here. 35 meters of water can find these beautiful red tree corals. And we'll not look at this video, but they provide habitat for other fish. They also provide insight into many ecological processes because corals can live 200-300 years long. So we can take samples of corals and we can get information using stable isotopes about the history of the environment they grew up in, the temperatures of the water they grew in, the mineral composition of the seawater they grew in, as well as study their role ecologically providing habitat for other species. So who is this guy? Jacques Cousteau. I've met Jean-Michel Cousteau. I never got to meet Jacques Cousteau, but this is James Cameron in his Jacques Cousteau form. This is him after months of preparing himself mentally to dive in the deepest undersea trench in the world. He had been in close contact with Picard before Picard passed away. He spends a lot of time with Don Walsh. he did his homework. I was actually very impressed. For everything else he's doing in his life, James Cameron did a stellar job in studying not only the physics and the science behind deep water diving, but he also had that curiosity that takes him so many places in his life, and he totally focused it on getting down into the Challenger Deep to try to expand our knowledge of the deep ocean in a way that is very difficult to do. You know, we're investing in NASA, we're going to the moon, we have satellites everywhere. How many deep diving submarines do we have? Maybe 3. You know, we really have very little knowledge of what we like to call inner space. And that comes from decision making, where we put our resources in this country. And so here he had an opportunity, being a very wealthy filmmaker, to hire some specialists to design this sub, and then he had the wherewithal to pilot it. And Cameron did so just a few years ago. And his dives, I'm going to cut right to this because you're going to go see more about his film. His dive into the Marianas Trench was very successful. He dove down. He had some failures of equipment like we experienced at shallower depths. He had hydraulic problems. He had engine battery integration issues. His navigation was excellent, but it was pretty risky in undertaking. And he did it to expand our knowledge of technology. One of the huge tests he was doing was with this what's called syntactic foam. How do you maintain a sub that's relatively small, not the size of the Trieste? His sub is a fraction of the size of the Trieste, and get it back to surface. Well, you need something that floats because your thrusters are never going to get you up there in time. You know, I told you it was about an hour and 20 minutes to get 1,000 meters. Now go 11. He's gone, you know, over 10 times as deep as I'm capable of going, and it takes a very long time unless you have a specially designed system. There's not enough battery and power and thruster power to get you back up in a reasonable amount of time from a dive like that. So this special foam was actually made of glass beads and this special resin coating. So he and his team actually used titanium knowledge, basic physics about the spheres, and built this sub also with lots of lights and cameras and collection technology. And this is one of the species they collected. And Hirundella gigas lives in the Marianas Trench. And I told you earlier that a lot of species are migrating daily and that we are connected to deep sea creatures more than we might observe on an everyday basis. And this is one example of this. After Cameron did this dive and collected these creatures, he sort of inspired a guy in Britain named Alan Jameson to drop down there again and get more samples of this very same species. And when Alan did that, he said, I want to know a little more about them. I'm going to do some chemical tests. I'm going to share these with my environmental scientists that do chemistry work. And he tested this species. Alan tested the species found by Cameron and looked at PCBs, DDT, chemistry, chemicals we know of. We've heard of these, haven't we? Why? Because humans made them. He also looked at a special group of compounds that are flame retardants. Pretty heavy-duty organic chemistry that we have created for various human needs. And they found in the Marianas Trench, just published last year, these creatures were the highest of any organism ever tested anywhere on the planet in PCBs and in these flame retardants. So our reach, you know, we're connected to the shallows. These creatures are moving up and down. Water currents are moving. But deep places are where toxins can aggregate. They're far out of sight. But this does happen, and we affect those creatures that are even in the most remote part of our little blue planet, and it's just something that's illuminating. It was interesting. We had no idea. You know, we've gone to deep places and found that some things concentrate there, but when these findings came out, it was a little sobering, but it's certainly informative about the decisions we make and what we produce, how we treat the ocean around us, because it's the same water that our salmon swim in, that we swim in, that we like to harvest from and appreciate the wildlife in. It ends up that we have some similar species right here. This is a very similar species at just 10 meters. Enoch Bay lives inside a jellyfish. So these species are shallow and they're also quite deep, and they're the base of the food web for so many creatures. So something Cameron hoped to see and has seen in his mind's eye, and you'll see this in the abyss, is bioluminescence. Okay, we talked about creatures having these relationships with bacteria to make light. We have ctenophores. You're going to see some of that in the film, that even though our knowledge of creatures that create and put out light for various purposes was very new in the 80s when Cameron made the film Abyss, it really influenced his ideas, his dreams, and then his creative energy in generating this huge stage that takes you down into the deep. And he wasn't too far off, amazingly. I first saw it and I was like, I don't know. But now that I've gone down in submersibles and shut off all my lights and see the bioluminescence out there, it's pretty incredible. So we have up here ctenophores. We have the anglerfishes created from the mind of Ray Troll, but based on science, these relationships of fish and bacteria. And then we have what my great friend Edie Witter has found. This is one single creature. This is just one of many species. She's come to find and publish in Science about 90% of all creatures in the ocean exude light. That's one animal in about 1 minute, changing its form, changing the light. Amazing. And so in medicine, we have a lot to learn about this process, especially in the case of creatures like anglerfish, because it's bacteria and a vertebrate saying, hey, turn on your light, turn off your light. How does that happen? Well, there's this process called quorum sensing in the bacteria where they all have to do the same thing. It's like if one bacteria lit up, it doesn't do much for you, does it? They have to all light up. And if we can learn what that mechanism of communication is from vertebrates to bacteria, we may learn more about cancer. We may learn more about disease, about how to capture that process and apply it to medicine to say, let's switch off those bad cells. Let's switch on those good cells. This is an area of medicine and deep sea research that's really fascinating, and I hope in Alaska we get further into it. And these, again, creatures use light for all kinds of reasons. Okay, this guy has chromatophores. These light up. The shrimp lights up, but the shrimp's not saying, hey, light up, come and find me. No, they spit out this bioluminescent puke, and the predator is distracted. Okay, and then the shrimp gets away. There's all kinds of uses we're finding for all of these different types of things. Okay, so in a few minutes, those of you fortunate enough to have time to go over to the Goldtown Nickelodeon to see the film Abyss are going to see more of how this guy thinks. This is James Cameron's Submersible. He went to the trench in. This is some of the charts. But these are the things that were only dreams at that time. He made that film over 20 years ago. And then he did it. And he saw creatures like this for the first time in real life. This is Cleone limacina. And you can see at the end of the film in the abyss, creatures that he created, which we only had an idea about, an inkling about. And he, as a creative, curious filmmaker, was able to capture some of those concepts of these deep sea creatures, including their bioluminescence and how they move, into his film. And it's really fascinating. Plus, he has lots of great submersibles and ROVs in it. So this is a species that is a lovely small flying snail, a pteropod. This is the base of the food chain for a lot of salmon in Alaska. They have a tiny shell inside. There's a lot of ocean acidification studies focused totally on this. How could James have known it was so important? I don't know, but watch for this in the movie if you get to go and see it today. Okay, I think I better stop there so folks can get to the abyss. And you'll also see this very submarine. Like I said, it's in the movie. Doesn't look quite the same, but keep your eye open for it. If you have any questions, feel free to ask me. Otherwise, if you're ready to get up and get ready for the great film, The Abyss, at Nickelodeon Theater, feel free to stand up and make your way across the street. Thank you. I want you on my crew, you guys.
We'll take a couple questions before Michelle takes off to go over to the Goldtown.
I wondered, when you're sampling these long-lived corals, have you been able to observe any effects of climate change at the great depths, or is it attenuated by the depth?
Well, corals, growth rate, the growth rate of corals can be related to temperature in some ways, and also related to productivity, so their access to food. What's actually, I mean, there's so much we can talk about. What's more interesting for looking at changes in climate was something that was a complete surprise. Collected these what's called incipient concretions, these sediment clods down at depth, 200-300 meters deep, and they were full of diatoms. Some of the diatoms were ice algae diatoms. We were able to look at the ratio over time for the last 15,000 years, which is since the last little ice age in the Bering Sea. You know, the Bering Sea was low, and there was Bering Land Bridge, and some of this area, we looked at the ratio of sea ice algae and non-ice associated algae, looking at those ratios by the species assemblages over time, that and using what's called an isotope of oxygen, the ratio of oxygen of some forms of the oxygen element can be compared to one another to look at the temperature of the water. And so we incorporate that, and we have temperature and ratio of microalgae, and that's what we use to look at changes in climate over time up there, and it was a total surprise that we were able to do it without having to drill cores. The coral is a little bit more complex because it relates to productivity as well as temperature. Does that answer your question?
Yes.
Okay, great. You're welcome. Yes?
Michelle, so is there any relationship between the PCB and those bioaccumulants with regard to anthropogenic inputs? I mean, is it possible that those could have come from some other natural...
The PCBs?
Yeah.
Alan Jameson, who I had the great pleasure to meet in Aberdeen, Scotland in 2011, did basically, the question was, do we know those PCBs are human-made, or could they possibly be natural? And the short answer is he did the chemical fingerprinting to link those that he was quantifying to human-produced PCBs. And they were quite high. Now, this is a deep area, and as you know, there's one huge conveyor belt in the world's oceans. Anybody know where it's considered the oldest seawater? It's the Aleutian Trench, okay? And we haven't even been down there. Side note, Cameron, who I've met several times, after he did this great dive, I said, so now what about that sub? And he loaned it to Woods Hole, and he said, well, we could make it available for research. He said he basically would loan me the landers and the sub for use in the Aleutian Trench to try to learn about what's down in the cold water here. Unfortunately, Woods Hole was transferring that sub, and they torched it. Caught fire. Yeah. But Ron Allen, the designer of that particular submersible, is alive and well, and for just a few $1 million, he'll build one for me too. But the landers are available, and the landers are quite handy too. They have all those super deep water housings and sampling and cameras, so we may be able to use those. It's not as interesting, but then we can take a look at some of these things in our own waters. We know we used to have a lot of military activity in the Aleutians, a lot of the military, stored goods, shall we say, chemicals and bombs and things like that. War's over, what are we going to do? Haul it back to America? Where are we going to put it? No, just chuck it in the deep ocean. That was the thinking at the time, and there's quite a bit of it in certain places down there we might encounter. But there's also amazing things like deep diving whales, like the new species of beaked whale we just discovered, and creatures we haven't even ever seen. So there's both things to learn about ourselves, looking in the chemical mirror, if you will, and things to learn about the natural world that we have never experienced. So hopefully we will get there. Any other questions before we go to the movie? Okay. Oh, yes, Katie.
Do you think Cameron accomplished his goal?
Did Cameron accomplish his goal? James Cameron's goals were largely threefold. One, survive. Bingo, did it. Two, to contribute to submarine technology that had kind of stalled out globally and especially in the United States. He did that. The sub, it did, at depth, that fancy syntactic foam that was extremely expensive to make, that whole thing shrunk 2.5 centimeters. And I mean, you do shrink. I mean, even titanium, I've been in a titanium hull and gone down just 500 meters, and all the latches and everything that held me in as I'm being put on the surface to let go, and I go down in the cold water, and it So they do shrink. I've seen buckles just fall right off. You're like, ah! And then you think, oh, wait, under this pressure, I'll never get out. It's not going to open. But the syntactic foam did shrink. So there's a little bit more work to do. But on the technology side of things, I think largely mission accomplished. He did have failures of a couple of his manipulators. We wish there were a couple samples we wish he had gotten. He just couldn't because the hydraulics, super high pressure, they just failed. His camera systems all worked. As far as contributing to science, he wanted to see more huge creatures. You know, he has a fantastic imagination. The deep sea, not, you know, the density of large creatures like that was less than he might have wanted to see. But some of the spin-off effects, he's keeping 12 students at Scripps busy, nonstop Scripps Institution in California, studying all the creatures, microbes to copepods and amphipods he collected and other species, keeping them busy, and many new species are coming out of that. So largely successful, especially on the go down and come back part of it. Yeah, thanks. Any other questions?
I just had a quick question about how glacial fjord systems are aiding the deep sea research, just cold water and
Well, glacial fjords are awesome because they're like a miniature deep trench. They're like the whole thing in small space. Like we have many glacial fjords carved by glaciers, left deep, and often with many sills. And we know that like the deep sea, we're finding that they do also have their own sort of retention mechanisms. They're almost like little isolated communities. So the deep ocean is somewhat isolated from the creatures in the deepest part of the ocean. The hadal pelagic zone are kind of genetically isolated, and in glacial fjords we see that same kind of genetic isolation. And genetic isolation leads to some really cool creatures evolving in isolation. They may have branches in evolution to species we're more familiar with, but in that regard the glacial fjord systems teach us a lot about what gets retained in deep systems and about how creatures in semi-isolation evolve independently and are reflective of that specific and unique microenvironment where they live. Is that helpful? Did you have another track you were thinking on?
I was just curious, just because, yeah, it's
There are a lot of parallels.
yeah,
for
it's
sure.
definitely like a remote from the other deep sea. It's cold, and the species are hopefully a little bit hot, closer to the surface.
Yeah, they're fantastic systems. The whole ice systems, whether it's sea ice or glacial ice, and that sympagic zone, so it's like looking up. You go to the Arctic and you're underwater and you look up, and the sympagic is that underneath part of the ice. That alone is its own massive environment we're finding out, because the sea ice and the glacial ice both have these tiny channels, 1 millimeter in diameter, and they're loaded with special creatures that live only in those channels and kind of emerge under that ice layer, and that becomes its own unique habitat. So glacial fjords allow us to kind of study what's up in the far north to understand sea ice dynamics in more localized areas. And we have a lot of species that are very isolated in these fjords, like the blue king crab. They're kind of an ice-associated creature. They only eat the algae that grows on the bottom of ice when they're very tiny. And so they grow only in the sea ice and only in the deep areas of the Bering Sea and in these deep fjord ecosystems. So there are some parallels with glacial fjords, even though they don't have as much salt injection as the North Sea. So, well, thanks everyone. I hope you all get to go to the abyss. Enjoy Cameron's movie. Thank you.